Welcome to Shanti-Peace for Mathematics. In the previous video, we have talked about the continuous function, which tells you that if you have a function which define over D to C, where D is a subset of C and Z0 belongs to D, and this Z0 contains a neighborhood of Z0, and then if you want to say that f is continuous at the point z0, if it has to be satisfy three conditions. The first one is limit of f of z as z tends to z0 is exist. The second one, f of z0 is exist, that means at point the function has the value. And the third one, limit of f of z is equal to f of z0 as z tends to z0. And all these three conditions also can be written in the form of as for every epsilon greater than 0 there exists a delta greater than 0 such that mode of z minus z0 less than delta implies mode of f of z minus f of z0 less than epsilon. And then we have discussed certain results on a continuity. Now we are ready to introduce the derivative of a complex valued function. For the real valued function, the derivative is defined in the manner that limit of f of x minus f of x0 upon x minus x0 as x tends to x0. Then we can say that f is differentiable at the point x0. So it is nothing but the difference of f in the numerator, difference of x in the denominator, and this is the instantaneous limit is there, so that's why it is instantaneous rate of change is there. The same idea will copy and define a differentiable function for complex function, that is f of z be a function defined in some neighborhood of z0. We say that f of z is differentiable at point z0 if limit of f of z minus f of z0 upon z minus z0 as z tends to z0 exist and finite. And this limit is denoted, if this is exists, then it is denoted as f dash of z0. So that is value is f dash of z0, and we say that f dash of z0 is the derivative of the function f of z at point z0. Further, we say that the function is differentiable on the set S in a complex plane if it is differentiable at each point of that set. Now this limit star we can also write in the terms of epsilon delta definition, that is as for every given epsilon greater than 0 there exists a delta greater than 0 such that mode of f of z minus f of z0 upon z minus z0 minus f dash of z0 less than epsilon whenever 0 less than mode z minus z0 less than delta. And since we have this, we can write it is in the epsilon delta definition, we can define one function, that is eta of z as f of z minus f of z0 upon z minus z0 minus f dash of z0 if z is not equal to z0 and 0 if z is equal to z0. That is, I am defining this eta function on this neighborhood, that is all z such that mode of z minus z0 less than delta to c, I am defining as this way. So what is the domain of this function is the neighborhood. So in that neighborhood, whatever the neighborhood of z0 we have, that on that neighborhood I am defining the function in this manner, that is this quantity I am taking, that is putting here. So due to this condition, what we can say is this limit eta of z is nothing but the eta of z0, which is 0, because if you take the limit due to that as z tends to z0, we will have this. So we can say that eta is the continuous function at point z0. So by definition of continuity, by epsilon delta definition, we can say that for every epsilon greater than 0 there exists some delta, and delta is exactly this what we have. greater than 0 such that n eta of z minus 0 is less than epsilon for every z minus z0 less than delta, that we can say. And due to this, what we can write this expression as, that is eta of z, we have it is f of z minus f of z0 upon z minus z0 minus f dash of z0, and if I multiply both sides by z minus z0, then we can write this is z minus z0 into eta of z equal to f of z minus f of z0 minus f dash of z0 into z minus z0, and this is true for every z minus z0 less than delta. So if you can make this equation as f of z equal to, we can have this equation can be written in the form of f of z0 plus f dash of z0 into z minus z0 plus eta of z into z minus z0. We call this equation as equation 1, and this is true for every z it is in that neighborhood. So we'll use this result later on. Let us give some another way to represent your definition of the derivative. If you consider z minus z0 is equal to delta z, then above definition, that is limit of z tends to z0, f of z minus f of z0 upon z minus z0 equal to f dash of z0. This definition can be rewritten as delta z tends to 0, as z minus z0 is delta z. So if z tends to z0, the delta z will tends to 0, and instead of z I may write as z0 plus delta z. So that's why it is f of z0 plus delta z minus f of z0 upon delta z equal to f dash of z0, and this is true for any z point z0 in general. So that's why we usually write without this z0, without this suffix 0 here, we'll write limit delta z tends to 0, f of z plus delta z minus f of z upon delta z equal to f dash of z. So this is the things. The next thing we can write is, if w you can consider as f of z, then what is delta w you may consider as f of z plus delta z minus f of z. So this definition can be written as dw by dz is equal to limit delta z tends to 0, delta w upon delta z equal to the same limit will have limit of delta z tends to 0, f of z plus delta z minus f of z upon delta z. So it is actually a change in w upon change in z, and due to this limit it is instantaneous change is there. So that's why it is instantaneous rate of change you will get. Now with this different form of the definition of a derivative we have seen here. After that, let us talk about some examples. So the first one is prove that f of z is equal to z square is differentiable for every z in C, for every complex number. So as per the definition, what is we have for any z in C, what is limit of deltas w upon delta z tends to 0. So as per the definition, we'll say this is delta z tends to 0, f of z plus delta z minus f of z upon delta z, and what is f of z is z square. So z plus delta z will gives you z plus delta z whole square, and f of z is z square upon delta z. As delta z tends to 0 you have. So if you just expand this z plus delta z, it will gives you z square plus 2z into delta z plus delta z square minus z square upon delta z. So you just notice that the z square will get cancelled out, and you will have, that is limit delta z tends to 0, and delta z is common out from this two quantity, so it will have 2z plus delta z upon delta z, and delta z is cancelled out from the numerator and the denominator, so you will have delta z tends to 0, 2z plus delta z, and that will gives you 2z. So that means this is f dash of z. So what we have proved is here is f of z is z square, then the f dash of z is 2z. I am giving you this is as an homework, that if f of z is z power n, n belongs to n, then prove that f dash of z is n into z raised to n minus 1. So try to do this by yourself. Now let us go to the next example. So that f of z is equal to mod z square is differentiable only at the origin, otherwise it is not differentiable. So for any z in C, what is this limit delta z tends to 0, delta w upon delta z will gives you limit of delta z tends to 0, f of z plus delta z minus f of z upon delta z. This will gives you limit delta z tends to 0, mod of z plus delta z square, because this is the function f of z is mod of z square minus mod z square upon delta z, and you know that mod of z square can be written as z into z bar. So due to that we can write this is as limit delta z tends to 0, z plus delta z into z plus delta z bar minus z into z bar upon delta z, and you know that z1 plus z2 bar we can write as z1 bar plus z2 bar. So that's why we can write as delta z tends to 0, z plus delta z into z bar plus delta z bar minus z into z bar upon delta z. This can be multiply the brackets and can be rewritten as limit delta z tends to 0, z into z bar plus, so this will multiply to this one, plus z into delta z bar plus delta z into z bar plus delta z into delta z bar minus z into z bar upon delta z, and you just notice that z into z bar will be cancelled out. So you will left with the quantity, and if you divide this delta z to this, you will have the first one is z into delta z bar upon delta z plus z bar, that is delta z is divided by delta z. Here is also delta z is divided by delta z, so we will have delta z bar. So this is the quantity you will have here. Now at point 0, so now if you consider z is 0, then dw upon dz at z is equal to 0, you will have is limit delta z tends to 0. Because z is 0, you will have 0 here, so it is 0 into delta z bar upon delta z, plus if z is 0, so z bar is also 0 plus delta z bar, and since delta z is tending to 0, delta z bar is also tending to 0, because what is delta z is delta x plus I delta y. What is delta is nothing but the increment in z, so it has to be increment in real part and increment in imaginary part. So what is delta z bar? It is delta z minus I delta y. If this is tends to 0, that means delta x tends to 0, delta y tends to 0, so delta z bar is tends to 0, and this is 0, already 0 into some quantity is there, so this is 0, so that finally you will have 0. So at z equal to 0, the limit is exists, so we can say that f is differentiable at the point z0. Now what will happen if it is non-zero points? So if z is non-zero points, then that is limit of delta z tends to 0 is this. Now I may write down delta z as delta x plus I delta y. So this equation I can rewrite in the form of as z delta x minus I delta y upon delta x plus I delta y plus z bar plus delta x minus I delta y. Now I am choosing the path, or I can take a repeated limit. So because this delta z tends to 0, that I can write as delta x delta y tends to 0. So now I am taking the path as a repeated limits. So first I will show that the repeated limits are not equal, so that the limit is not exist. So I will start with the limit delta x tends to 0, limit delta y tends to 0, z into delta x minus I delta y upon delta x plus I delta y plus z bar plus delta x minus I delta y. So that can be written as delta x tends to 0. If you take the limit delta y tends to 0, we will have z. So this is delta x upon delta x plus z bar plus delta x, and as delta x will cancel out here, this will gives you z plus z bar, and the other side will have limit delta y tends to 0, limit delta x tends to 0, z into delta x minus I delta y upon delta x plus I delta y plus z bar plus delta x minus I delta y. This will be the limit delta x tends to, delta y tends to 0, z into minus I delta y upon I delta y plus z bar minus I delta y. Since delta y will get cancelled out and delta y tends to 0, the answer for this is minus z plus z bar. So when these two quantities are same, if z is non-zero, these two quantities are never equal to 0. So that's why, because z plus z bar is equal to minus z plus z bar, so this will get cancelled out. If z is 0, then and only then this is same. So if z is non-zero, then these repeated limits are not equal. If the repeated limits are not equal, we can say that f of z equal to mod z square is not differentiable at z is not equal to 0. Otherwise it is differentiable, that means at point z is equal to 0, it is differentiable function. So that completes the proof of this example or solution for that example. The next example, let us consider prove that f of z is equal to z bar is nowhere differentiable. So for that I am taking for any z in C, I am starting with limit delta z tends to 0, f of z plus delta z minus f of z upon delta z. I want to prove that this limit has to be exist. So for that limit delta z tends to 0, you know that z plus delta z can be written as z plus delta z bar minus z bar due to its definition of f, and as I have explained you, z1 plus z2 bar is z1 bar plus z2 bar, so that's why this we can write as, so it is z bar plus delta z bar minus z bar upon delta z. Z bar will get cancelled, so you will have limit delta z tends to 0, delta z bar upon delta z. So if you can write down this is in the form of delta x delta y, then this is delta x minus iy upon delta x plus iy. So now you can take the repeated limits here itself, or you can go with along the path delta x is equal to 0, then delta y equal to 0. So we'll have this limit delta z upon delta z bar upon delta z as delta z tends to 0 will gives you limit delta y tends to 0, that is minus I delta y upon delta y. So delta y get cancelled out, equal to minus 1. Along the path, delta y equal to 0, then delta x is 0. Limit delta z tends to 0, delta z bar upon delta z can be written as delta x tends to 0. Delta x upon delta x will gives you 1. Thus, by taking two different paths, we get two different limits. One time we'll get minus 1, other time we'll get 1. So therefore, the limit does not exist, and so the given function is not differentiable at the point z0. That z0 is any arbitrary point. So thus we can say that f of z is not differentiable at any point. So it is nowhere differentiable function. So let's go to the next example. Find the value of the derivative z minus I upon z plus I at I. So question is to find out what is f dash of I, where f of z is z minus I upon z plus I. So as per the definition, this is limit z tends to I, f of z minus f of I upon z minus I you will have. So that can be written as limit z tends to I, z minus I upon z plus I minus f of I. If this is f of z, then f of I is 0 upon z minus I. So this will gives you limit z tends to I, z minus I upon z plus I into z minus I. So z minus I will get cancelled. So that will gives you 1 upon I plus I. So that is 1 upon 2I. That can be written as minus I upon 2. So that is the derivative of this function at this point. Now the interesting thing here, what we can notice, that f of z is of the form u of xy plus iv of xy that we have, can be differentiable at the point but nowhere in the neighborhood of that point. What we have seen is f is differentiable at a point, but in the neighborhood of that point the function may not be differentiable. For example, we have talked about the f of z is equal to mod z square here. What is this function? This function is differentiable only at 0, except 0 it is non-differentiable function. So if you consider the neighborhood of 0, so any neighborhood of 0, so I can say that the function is differentiable at a point z equal to 0, but nowhere else in any neighborhood of that point. So here in this example, your u of xy is x square plus y square and v of xy is 0. So when f of z is equal to z square we have, it shows that the real and imaginary components of a function of a complex variable can continuous partial derivatives. So this has the continuous partial derivatives because they are continuous for all order, and yet the function may not be differentiable there. Okay, so you can just recall your advanced calculus course, and in that we have result that if that is a sufficient condition for differentiability. Here you can say that this ux and uy, u of xy and v of xy can have continuous partial derivatives, but function may not be differentiable there. One more thing we should notice, that this u of xy and v of xy are continuous function. That's why this mod z square function is continuous at every point, but the continuity of the function at a point does not imply the existence of derivative there. However, true that the existence of a derivative of a function at the point implies the continuity of the function at that point. So that we can state as a theorem as prove that every differentiable function, let f of z be a differentiable function at point z0. Now I'll starting with this f of z minus f of z0. So here I have to prove that every differentiable function is continuous. That means I am starting with the differentiable function and then I will try to prove that it is continuous. So for that I am starting with f of z minus f of z0. I am multiplying and dividing by z minus z0 here. So if you do this and if I take the limit both side as z tends to z0, if I take the limit here, then by limit rule, that is the product of limit is limit of product, we can write as limit z tends to z0 f of z minus f of z0 upon z minus z0 into limit z tends to z0 z minus z0, and this quantity will be f dash of z0 and this is quantity is z0 minus z0, so that's why it is 0. So what we can say is limit of this quantity z tends to z0, that is f of z, and this is independent of z, that's why it is f of z0 will have. So we can say that f is continuous at that point. So therefore f is at z is equal to z0. This completes the proof of that result, that every differentiable function is continuous. But the converse of this result is not true. That we already discussed by giving you example that mod of z square. This function is continuous everywhere but differentiable only at z is equal. With that note, I am making one more note here, that is the geometrical interpretation of the derivative of a function of complex variable are not as immediate as they are for the derivative of functions of real variable. Because in the real variable function you can say that if the function is not differentiable, that means it has a corner at some point. But here in the case of complex valued function, you cannot plot the graph of a function as I told you, so it is not possible to visualize that concept here. But we defer the development of such interpretation in unit 3 when we'll study about the conformal mapping. So with that note, we'll move forward with the another theorem, which are the rules of the derivative. The first thing, let us consider f and g are differentiable at point z. Then the first one, derivative of f plus g at point z will be del f upon del z plus dz upon dg upon dz. The second one, d by dz of c into f at z will gives you c into f dash of z. The third one, d by dz of f into g of z will gives you f dash of z into g of z plus d dash of z into f dash of z. And the fourth one, that is a division rule, d by dz of f upon g at z will gives you g of z square g of z f dash of z minus f of z g dash of z, provided g of z is not equal to 0. So let us try to prove the statements. Proof: d by dz of f plus g at z will gives you limit delta z tends to 0. As per the definition, we'll have f plus g z plus delta z minus f plus g z upon delta z. Now we apply the definition of pointwise addition. So as per that, we can write this is as f of z plus delta z plus g of z plus delta z minus f of z minus g of z upon delta z. that can be written as delta z tends to 0 f of z plus delta z minus f of z upon delta z plus limit delta z tends to 0 g of z plus delta z minus g of z upon delta z, and that can be write as f dash of z plus g dash of z. So that completes the proof of the derivative formula for addition. I am giving you the second one as a homework, and the fourth one is also as a homework. I will try to prove the third one here, and second and fourth one I am giving you as a homework. So proof for the third one that we'll discuss in this manner, that is f into g at z. As per the definition, we can say that limit delta z tends to 0 f into g at z plus delta z minus f into g at z upon delta z. So using the pointwise product of a function, we may write this as f of z plus delta z g of z plus delta z minus f of z into g of z upon delta z. Now you add and subtract some term here in between. So that is f of z plus delta z, g of z plus delta z as it is. I am adding the term and subtracting the term first. Z plus delta z into g of z, and add this term also, z plus delta z into g of z, and the last term is added as it is, f of z into g of z upon delta z. So that is, we may write as limit delta z tends to 0. Now you just observe that in the first two quantity, f of z plus delta z is common out. Inside bracket you will have g of z plus delta z minus g of z, and in the second two quantity you may see that g of z is common out. So the left quantity is z plus delta z minus f of z upon delta z you will have. Now this quantity I can write down in this form, that is limit delta z tends to 0 f of z plus delta z. Second one, limit delta z tends to 0 g of z plus delta z minus g of z upon delta z plus limit of delta z tends to 0 g of z into limit of delta z tends to 0 f of z plus delta z minus f of z upon delta z. Now in the first one, that is this, since given that f is differentiable, it implies that f is continuous. Since f is continuous, this delta z you can take, delta z tends to 0, that is this limit you can take inside the function. So that's why this gives you f of z. The second one, that is this, which is nothing but the g dash of z. The third one is independent of delta z, so that's why it is g of z as it is, and the last one is nothing but the f dash of z. So that's complete the proof of the product rule. Now next thing, we prove that the next theorem, we prove that the composition of two derivative function is differentiable, and due to that we have a chain rule. So this theorem will state in this manner that if f has a derivative at point z0 and g has a derivative at the point f of z0, and the composition function gof has a derivative at the point z0. Means a composition of a two differentiable function is a differentiable. Also, we have a chain rule for that, that is derivative of that composition function will be the derivative of g at f of z0 into f dash of z0. Now to prove this one, we'll use the equation 1 we have defined earlier. So let us recall what is the different equation 1 we have did. So this was the equation 1 we have discussed, where if f is differentiable at point z0, then we can write in this form, and this delta or nz will tends to 0 in that situation. So with the help of this, we may write here, given that f is differentiable at z0, so that's why we have f of z minus f of z0 equal to f dash of z0 into z minus z0 plus some function I am denoting as epsilon z minus z0. And given that g is differentiable at w0 is equal to f of z0, then we can write as g of w minus g of w0 equal to g dash of w0 into w minus w0 plus eta of w minus w0. Now if I call it this equation 2 and this one is 3. Now if I substitute the value of this 2 in 3, then what we can write this equation as, that is, so what I'm doing, I'm just putting the value of w. What is w is f of z. So what we get is g of f of z minus g of f of z0, because w0 is f of z0, that is minus f of z0. This is, we can write as f of z minus f of z0 plus eta of f of z0 z minus into f of z minus f of z0. But what is this f of z minus f of z0? Due to 1 we have this. So let us write down that value here and commoning out this quantity from that. So we have, that is equal to g dash of f of z0 plus eta of f of z, that is common out, and inside bracket the value of f of z minus f of z0 will be f dash of z0 plus epsilon of z0 into z minus z0. So this z minus z0 I can take it on the other side, that is g of f of z minus g of f of z0 upon z minus z0 equal to this quantity will have. I am taking a limit both side, as limit z tends to z0, the quantity gof at point z minus gof at point z0 upon z minus z0, and as you know that as z tends to z0, this quantity will tends to 0 and this quantity will tends to 0. So that's why it is g dash of f of z 0 into f dash of z0. That is the answer we'll have. So we can say that this limit is exists, that is a composition of a two differentiable function is differentiable, and we'll also get the chain rule for that, for the differentiability. So I can give you an exercise here, prove that f of z is equal to sine z square is differentiable everywhere. So try to prove this statement, and with this I'm giving you couple of more exercise to do yourself. Discuss the differentiability of the function f of z is equal to mod z square upon z if z is not equal to 0 and 0 if z is equal to 0 at origin. So with this, let us recall what we have did in this lecture. So we have defined the differentiable function in this lecture with the help of a limit, and we seen that there are different version of that definition. For epsilon delta definition with the help of eta, we also seen that, and with the help of delta z we also think the differentiability. We have seen that the rules of derivatives, that is a product rule, summation rule, division rule, or etc. We have seen that composition of a two differentiable function is differentiable, and that's it for this video. If you like this video, please press the like button. If you have any comment, suggestions or question, please drop down in a comment box below.